Hey there, today we'll be doing a problem called remove duplicates. Given the linked list, delete all nodes that have duplicate numbers, leaving only distinct numbers from the original list. Can you do this without taking up extra memory? So here we go. Let's check this out. In this problem, we have an input of 1, 2, 3, 3, 4, 4, 5, and then we have an output of 1, 2, 5. That means that any item that we have seen twice, 2 or more times, will be deleted. And the way we can delete it in a linked list is without taking up any extra memory is by sorting. If we create a sort and we have a previous pointer and a current pointer, and as long as the previous pointer is equal to the current pointer, then we can move it forward. If the previous pointer dot next, this 3 is equal to current dot next, that means they have duplicates. This means that we should move current and current dot next until they're different. That way we can point previous to current dot next and remove the 3's, and eventually we can move this again until we remove the 3 and 4's, and then we remove 3 and 4's, and we can just point 1, 2, and 5. This is a pretty, it will work effectively, and we will be able to solve this problem. So I'm guesstimating the runtime will be O of n log n, because we need to do a sort in order to sort the array. And this is the linked list, and this would require us to do a merge sort and a space-time complexity of O of, let's say, n, because of the stack by which we use for our recursive, to use our recursion to complete this process of merge sort. Because with merge sort, what we need to do is separate each item into its own pile and combine them together until we can merge all these items together. So I think we have talked about this problem a little while ago when we merged two sorted lists. We can use the same concept by merging recursively and merge each item multiple times over. So by that I mean, let's say we have 5, 4, 3, 2, 1. We separate these into we want to separate these into currently 5, 4 and 3, 2, 1. They're two separate halves, and now what we're going to do is put them together and separate them some more, and 5 and 4. So now there are two separate lists of 5 and 4, 3 and 2, and 1. And of course, this separates out to 2 and 1. And what happens here is when we combine these together, we will put the smaller one first and the larger one next. Of course, now we take these two lists and we combine them again, and now we have 1, 2, and 3. Same with this one. This one we have 4 and 5, and we have 4 and 5 again. And now we merge these two lists together to have 1, 2, 3, 4, 5. That's about it. So with that, we basically done our matching and our plan right here immediately as part of our understanding. And our match would be like a merge sort with a what do you call this thing? A previous pointer, current pointer function. Okay, with that, we are ready to go to the next step. Of course, we do need to talk about some edge cases. Edge cases would be probably something like empty. That's probably an edge case, and we should return nothing if there is nothing to return. And so I think what this would mean is that if there's nothing, then we should return, if there's not a head, then return not head. Yeah, just return that, and we should be good to go. So, all right. With that, we are done with our understanding here, and we are ready to write up plan. And it looks like we ran out of room, so we're gonna start writing our plan up here. What is our plan? Our plan is 1. We have to break list. So we should do a 1 merge sort, and this is 1.1. This is to break list down in half recursively until single item. To 1.2, merge items recursively. And 1.3, what we're going to do is return merged item, or merge sorted item. Okay, with that, we are done with our merge sort, and now we're going to do a 2, which is remove duplicates. And that it involves a previous pointer, 2.2, and current pointer, previous pointer dot next is equal to current pointer, then point to it, 2.3, otherwise previous pointer points dot next points to current dot next. We're talking about this issue here. Let's see, previous pointer dot next is equal to current pointer, or pointer dot next. Yeah, previous pointer dot next is equal to the current pointer. No, don't point to it. Then move to previous dot next. Okay, so we're missing an item here. So that item was to shift if previous. So suppose we're back here again, and we have current. If previous dot next and current dot next, if these next two numbers are different, then we don't have to move it forward. However, if however they are the same, previous dot next and current dot next, they're the same, the next two numbers are the same, move current forward. I think it's a while loop. Yeah, okay, with that, I think we're good. That's our plan. And we are ready to just complete this problem. Oh, one more thing. Let's just make a linked list item, because we don't have that. So let's get started. Let's make a class called linked list. And this class has an item. let's say init. Give me a moment. I'm just gonna go to lead code. So this is how you grab the list node. Okay, so yeah, I was having trouble thinking about that for a little bit because I haven't created a class node, linked list node in a long time, and that's where I remember it from. Okay, so we're at the 11-minute mark, and let's just keep moving on. Let's define our merge sort, and we're going to take in a head called list node. And we're going to return a head of the list node. Is that how it works? I'm not sure. Yeah, I think that's how it works. Great. Just like that. Okay, so let's return 0 for now, and let's run merge sort. Okay, great. So we do need to create a linked list, let's say this one, as one of our samples. We are now creating our list node because we don't have it. And we are creating our linked list as we speak right now. So okay, with that, our linked list is created, and we are ready to get started. Looks like a lot of this code is going to be pushed away. I will move the plan down because we don't have enough space to look at all of this. Actually, yeah. So okay, let's get started with our merge sort then. We do have to have a split half. To get the halfway point is to basically like get a fast and slow pointer. So slow, so like we're just gonna be while fast dot next and fast dot next dot next. If that exists, slow is equal to slow dot next, and fast is equal to fast dot next dot next. So this way we just move items forward, and then we can return slow dot next this would be our midpoint. Because if you have any linked lists and you have a slow and fast pointer, if you move twice and you move once with the slow pointer, you will see that the slow pointer always ends up at the middle by the time the fast pointer reaches the end. Okay, so we got the half point, and we do need to define the merge. So how are we going to merge? We have to merge two lists, list 1 and list 2. And then we're going to return one single list node. So I think this is pretty self-explanatory. So list 1 pointer. This is going to be a very long video, huh? Yeah, because I think there are multiple, well, no, I don't think, I know for sure that there are multiple problems in this because we have a merge sort, remove duplicates. We can find both of those problems in leak code. So if you do need to go back and check leak code, we can do a merge sort. So we do a merge two sorted lists, and we also do a duplicate, remove duplicate, and it's number 2. So with these two problems together, we are able to like solve this problem. Yeah, but this is not, merge two sorted lists is not exactly the right problem. It's I think the problem is sort list. Leak code. Yeah, that's the problem. So we need to do this problem and this problem. There are two different medium problems involved in this one problem. And we also have to create our own linked list. So if you're giving this in an interview, this will take you quite some time. Okay, so back to work. So this one, list 2. And so what we're gonna do is make sure that if list 1 while list 1 pointer and list 2 pointer, so they're still pointing to something, list 1 pointer is dot value is less than or equal to list 2 pointer dot value. What's going to happen here is we have to have a dummy node. That's set to 0. It doesn't matter what it's set to. We can just set it to nothing. But we just need to send, and we need a current node. So we can send it forward. So current.next is equal to list1 ptr, and list1 ptr equals list1 ptr.next. And so we're merging the two linked lists together. Current dot equals current.next. Else current.next is equal to list1 ptr, list2 ptr, and list2 ptr is equal to list2 ptr.next. We're moving it forward, and current equals current.next. So with that, we have merged two lists, and if anything if list1 ptr, then we're gonna attach that to the end. Otherwise, we'll attach the other part. Sorry about that. So then we return dummy node .next. Okay, great. With that, we do have a little bit more to go to get this function working. And that is to, well, I think we're able to run this function like this. So we just need to run, so we have head, right? So we need a list1 is equal to head, and list2 is equal to get half at the head. And now what we need to do when we get that, it is we need to break off the chain. So let's say 1, 2, 3, 4, 5. And what happens is that this is still connected, right? These items are connected. So suppose we get half, right? Slow.next. So we're right here right now. And this is where our half starts. This is list 1 and this is list 2. Okay. What happens here is that we need to split. We need to make sure that this no longer connects to this part. Okay. So how do we do that? Well, one way is to make sure we disconnect. We can disconnect this part because, and then we'll end up with this. So I think we just grab slow then. So that way we're here, and we get this is going to be our temp, and now we disconnect this part. So what I mean is, so temp equals list2.next. List2.next is equal to none, and that disconnects this connection here, and we set list2 equals temp. Now list2 becomes temp, and we start off here at the 4, right? Okay, so now that they're disconnected, what we can do is we're gonna run merge sort on both sides. So list1 equals merge sort of list1, and list2 is also equal to the merge sort of list2. So this breaks down these items and continually break them down until they are nothing, and we can return the merge between list1 and list2. The thing is, what we need to do is a base case, because when we're doing recursion, it is important to do base case. And what we're gonna do is, if not head or head.next is none, then we're gonna return our head immediately. That way we return the single item. With that, I think we are done with merge sort. Okay, just in case we make sure we got this correctly computed, let's send it into LeetCode, and make sure this works. Of course, during an interview, you won't be able to send it in to LeetCode to make sure it works. We're going to have to make sure it works by actually testing their code. Yeah, so it looks like we do need to move all of this code up. Oh, merge sort doesn't exist here in this world. So it does work, and let's submit it. Perfect. So it is a functioning code of merge sort. And so, of course, we could test this in using this type of code. And so what happened, let's go over it. Okay. So we do need to move some of this code around. Give me a moment. So let's just go through one example and then we'll move the code around. So we have this list 5, 4, 3, 2, 1. But what happens here is we get two parts of the list and we split it in half. Then we return list 1 and list 2, merge sort that. So basically we're going to split that in half again and split that in half again until we have a single item. In this case, this has a single item. It turns, and what happens is we'll merge those and make them equal, like even, like sorted in ascending order. In this one here, we're still not broken down into a single item yet. So we'll continue breaking it down until it is a single item. And then we can merge these two together when they're equal. So now we have 1, 2, 3, and 4, 5. And we merge these two again to get 1, 2, 3, 4, 5. Perfect. With that, we are good on this end of our code. And we're ready to move on from merge sort. Okay. So we need to now remove the duplicates. Wow, this is a very long video. So we're removing duplicates from a linked list that's sorted already in this case. So we do need to merge sorts. We'll merge sort the head and then remove duplicates in the and we also need to print this item out, and so we do need a print linked list function as well to make sure, or we can define it here. So we're printing the linked list, and we're taking in a node called head, and we're going to print head.next. And this is going to do a print of head.val. And this will print the whole entire linked list downward. That's good enough. Okay. Now we need more space. Okay, so we have more space now. So we're gonna have to remove duplicates. So what was the plan? The plan was to create a previous pointer and a current pointer. So previous is equal to, let's say, a dummy. Let's create a dummy node, because the first item could be, a duplicate. And so dummy node equals list node. Current node equals, well, we need to attach the dummy node first. Which is equal, equals head, and current equals previous.next. Perfect. With that, we have created our previous and current pointers. So we do need to move the current pointer while there's a current exists. We're going to move these items forward. I think we have a clear example about how to do this here, and we're going to grab that. So make sure we're coding properly. Okay, so while current and while previous value dot next dot value. So here we start off with a dummy node, and the dummy node and this current node dot next are different. So previous node dot next dot val equals current dot next dot val current equals current dot next. Okay, so they're not equal. So if previous dot next is equal to current, so if these are the same, then previous equals previous dot next. Of course, we move current equals current dot next every single time. So we set previous to be previous dot next, and we set current to be current dot next. Okay, now we see that they are different again. So this will never occur. And we'll move this forward one more time. As we can see here, previous is equal to pointing to the next item, previous dot next, and current dot next dot val. They are the same, so we move current forward until current dot next is no longer the same. So 4 and 3 are no longer the same. So now we point previous to current dot next. And with that, we have set that up properly. So now what happens is that we remove the connection from, we just basically direct point the previous dot next is now equal to the current dot next, which is 4. And then we've set current to be current dot next. And so we're here now, and basically this removes this chunk right there. And so the same thing happens here when we move the current, and that means we're going to point 2 to 5 now, so directly to 5. And with that, and we move the current to be, at 5, and current dot next is equal to none. So what happens here is previous dot next is equal to current, and what happens is previous equals previous dot next, and current equals current dot next, and that will be pointing to none. And that way, we are done here, and we can return a single item, dummy node dot next. And with that, we have completed this part of the problem as well. And we also have done the review about how it works. I don't think there's anything other than this much. So let's just take this code and put it into delete code and make sure it works. So run. While current okay, it looks like it's working. All right. Okay, it looks like what happens here while current and all right, great. So we basically made a couple out of bound errors, but we've resolved those, and we have solved this problem. So now what we have here is a solution, one solution with all of these items, and we have this head here. So what we do need to do is print. I don't think this is a good function in linked list. So what we're gonna do is just move this down here and create another print function. Always a base case with recursion, and we are heading into a 40-minute video, and so this is definitely a long problem. So we're going to print the head here and print the head afterwards. Let's run it. What's the problem here? Okay, yeah. Let's just remove that part. I see. Okay, so right, we have to run print LL. My bad. Okay, so we have 1, 2, 3, 4, 4, 5, and then now we have just 1, 2, 5. So it has worked properly, and we were able to solve this problem. Of course, this is a lot of code. You can find this code in this repo where you see this video, and you can check it out. So with that, let's get into the last part, our evaluation. Of course, there's more tests you can do. Let's set the head to none, and let's just run that. Well, there's no way to set it to none, it seems, because I've programmed this to, well, I think you can. So just remove duplicates, none, and print that. Yeah, just nothing's printed, but it works perfectly fine. So that's tested. So let's finish this off with an evaluation. So the evaluation is we spent the longest time that we spent was merge sort, which is n log n for all the items, and then the remove duplicates took O of n time, but the longest time is going to be n log n, and the space required was the recursion, and that took O of n space. And that's about it. Yeah. So if you have any questions, please comment below. If you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. And I will include all of these links with the lead code, and I will also include the link with the REPL. All right, see you in the next one.